Okay, I want to clarify something. This is not from Pedro Valdes Sosa, it's from Pedro Valdes Hernandez. So he wasn't able to be here.
I apologize profusely.
No problem, he's my son. And I'm here covering, so any mistake I do, it's my fault. Okay, so this is an investigation into how to try to estimate negative bold responses differentially in different subjects, and to leverage to try to identify mechanisms, especially in epileptic patients. What is the strategy? Well, the first is to look at possible mechanisms for the negative bold response. This has been observed in both task and, let's say, block designs, also in epilepsy, especially by the group of Gottman. But there's little clarity of which of the possible mechanisms could be operating. So in this work, there's 4 mechanisms that actually lead to 5 possible ways of looking at this. One is an extension of Friston's balloon model, of the extended balloon model, and is based on lateral callosal inhibition. It also leads to a possible mechanism by neuronal disruption of activity of the resting state. There's a second group, or the second model, which would be arterial blood stealing, and you can see that in B. Additionally, and with the term that was introduced by Bandettini, there is the possibility of vein blood back pressure. Finally, there's a dysregulation, a possible dysregulation of balance between neurovascular and neurometabolic coupling. Okay, we have these 4 mechanisms. We have the set of differential equations that characterize each of them. We can then actually look at the dependence of these possible mechanisms of the bold response and changes that are associated between the mechanisms and certain parameters of the whole model. And this is what we're seeing in this slide. What you see there is for the positive response and for the negative response regions, what is happening and how we change for every one of the 4 mechanisms, the parameter that is most closely related in the differential equations to them. And we see that there's a characteristic where the arrow is where we see the change specifically that is most pronounced for the negative bold response. For, let's say, for stimulation in a task, in a block design, it would go like this, which is very similar. I want to call your attention once again to the lower row, which has the bold response. And this, in a task-related response, could lead in for example, in the dysregulation or in the lack of balance, to not observe the negative bold response. Okay, so what we've shown here is with the differential equations that the specific parameters can be moved, and this is a set of plausible models. How can we use this for actual analysis? We embed this into a state space model. And here we're using the local linearization technique that the Cuban Neuroscience Center and the Institute of Statistical Mathematics developed over the years. And this allows us to produce simulations of the activity by solving a nonlinear stochastic differential equation within the framework of a state space equation. Here we see the producing randomized stimuli. You can see on the top the relation between simulated and estimated responses by this mechanism. You see it is quite tight. On the lower row, this is a different vision of the same set of 1,000 random shocks, and you can see that the estimates, and they're shown there for the full, for 2/3 and 1/3 of the data. You can see that the let's say the nominal and the estimated values are quite close, and actually they're tightly non-dispersed around the true value. So we have both accuracy and precision. Well, if this works, we can now produce with these stimulations, we can produce a way of looking at actual data. So what we see here is in a glass brain, different regions that have actually different types of mechanism for a negative ball response. And what you see below on the left in B is the design matrix for an SPM. And what this allows us to do is to pull out the regions where there's maximal intensity of the model to produce a negative ball response. And you see that in the simulation, and still simulation, you can see that the areas are picked out quite correctly, and that the shape of the, let's say, impulse response is the adequate one for each of the 5 different instances that we have proposed for mechanisms of the negative ball response. Now, what is the next step? Okay, we're able to pick out the regions, estimate the impulse response. I have to mention that we're using a linear impulse response. The difference with a nonlinear fitting of the impulse response is minimal. Here, what we're doing is constructing with these 1,000 simulated points, with we're using something where we're embedding this local model in a larger model using something that was developed and is known as the nearest neighbor autoregressive with exogenous input model for fMRI. And this was published a number of years ago. This allows us to do a spatial, over the whole brain reconstruction, taking into consideration local connections. Now, using that model and using the design matrix that was constructed previously, and using quadratic linear discriminant, we use an ensemble machine learning technique to differentiate the different types of responses. It is to be noticed that the neural dysregulation and also the lack of coupling is well distinguished, but the lateral chiasal inhibition, the blood stealing and the blood back pressure are not that well distinguished. So already from the characteristics of the model, we have an idea of where we're going to get a good or a bad discrimination. Moving forward now to actual data, we apply this procedure, which, as I said, started out with looking at the capabilities of the neural models, of the different types of Windkessel models for the different processes, then went on to do simulations, and then went on to train classifiers. We can then apply a double procedure. One, to do a GLM analysis of the whole brain to find regions that are of interest, and then second, to actually look with the classifier to try to propose what type of negative ball response there is. So here we see one particular case. This is probably a disruption. This is an epileptic patient with this probable disruption of the default mode network. And there you see the estimated responses. You also see on the bottom, and so the localization on the top on the left, on the bottom, you see the following. You see the different spikes that were detected. That's in the row where you have the little bars. You see below, and I want to call your attention to that, in dark gray is the simulated response from the model that was fit, and in the bottom, the actual data. And the correspondence is quite good for this level of signal-to-noise ratio. Here we see another case. This is a case where there's actually activity, epileptic activity near a tumor. So this is a patient. You can see the tumors marked both by the red arrow and by the yellow circle. And once again, when you look below, you see in the middle these vertical spikes, which are the position of the spikes. You see the simulated response from the model, and you see the actual data. Finally, this is a third case where you see a different possible mechanism, and here, though there's no actual, let's say, discounting of the venous blood back pressure hypothesis, this appears to be more, and remember that we didn't get a good discrimination in the machine learning method between these two, but it is most probably an arterial blood stealing. So you can see here also the correspondence, and the idea behind this methodology then I think becomes clear. It is to train the classifier using the neural mass models and the Windkessel model according to the type, and then actually look for the location first with the GLM, and then try to classify specifically what type of negative Bold response this corresponds to. So in conclusion, we've studied several negative Bold response mechanisms. The crucial parameters in the formulation, not only do they, let's say, produce the effects we expect in the different models, they can also be estimated using the local linearization technique in a state space formulation. We can use the generalized linear model for the detection of the site and which mechanisms. We can distinguish quite well with quadratic discrimination, the neural dysregulation, and also the lack of coupling between the metabolic and hemodynamic phenomena, while the lateral and chiasal inhibition, the arterial blood stealing, and the venous blood back pressure cannot be distinguished well at this moment, but require additional information in future work, and we are investigating the presence of these negative Bold responses in epileptic patients. This may have implications for surgical planning and to look into the relevant physiopathology. So we invite you to look in detail at poster 1818, and you can direct your questions to the actual author of this, which is Pedro Valdes Hernandez, not Sosa. Okay, thank you very much.